Hello everyone, welcome back to my channel. Today we are diving into a fundamental topic in computer science, context-free grammars, CFGS and Chomsky normal form, CNF, the short one. These concepts are essential for anyone studying formal lines, automata theory, or even natural language processing. We will go through three key questions. First, I will show you how to construct grammars for specific lines. Then we will talk about grammar ambiguity, and finally we will tackle how to convert a grammar to Chomsky normal form. I will walk you through each question step by step and even show you Python code that automata parts of the process. Let's get started. Skip question 1 is construct context-free grammars to accept the following lines over 0 or 1. Explain your grammars. The lines W standards and ends with the same symbols. The part A and the part B. The lines W, the length of W is odd. Yes, I'm skipped. The question 1 is to construct context-free grammars. Introduction to CFG construction. Our first task is to construct context-free grammars, CFGs, for specific lines. CFGs are widely used in computer science, especially in compilers and parsers, because they can define the structure of lines grammar for lines with matic start and ensemble. In part A, we are asked to create a grammar for a line where each string starts and ends with the same symbol over the alphabet. Alphabet is 0, 1. Explanation of the rules. I designed two sets of rules for this one, where the string starts and ends with 0, and another where it starts and ends with 1. Here's what each rule does. Rule 1 is if you see that S goes to 0, A0, or S goes to 1, B1. These rules ensure the string begins and ends with the same symbol. A and B are non-terminal symbols that allow us to add any sequence of zeros and ones in between. Rule 2 is A, yes, this one. A goes to 0A or 1A or epsilon. The rule for A let us add any combination of zeros and ones, keeping the length flexible. The epsilon rule allows A to end without adding any characters, making it possible to have strings like 0 or 1. We use the Python code demonstrate to make this easier to understand. I think I wrote the Python code to represent this grammar. In the Python, we use dictionaries to store each non-terminal and its production rules. And show a Python dictionary representing a grammar. Each example is as the parenthesis 0A0, 1BA parenthesis, another one A0A or 1A or epsilon in the parentheses. By defining the grammar this way, we can easily check if a string matches the rules by following the prediction parts. And this is the explanation. And skip to part B. Part B is length W. The length of W is odd. For this length, we need a CFG that generates only strings of odd length over the alphabet, 0 or 1. And for part B, we need a grammar that only generates strings of odd length. Let's break down how we can do this. It is explanation of rules. Rule 1 is S, start symbol is S. S goes to 0A or 1A. This will ensure the string starts with a single 0 or 1. Since we want the odd length strings, each production step will add 2 characters. And rule 2, A goes to 0S or 1S or epsilon. Here each time A produces 0S or 1S, we add 2 symbols, preserving the odd length. Again, the epsilon rule allows us to terminate at any point with an odd length string. I think the Python code demonstration. Here is the Python code for this grammar. Each rule is designed to add symbol in the way that keeps to length odd. With this structure, we can generate all valid odd length strings over 0 or 1, the parentheses. And skip to question 2. Yes. Question 2, I'm reading the question 2. Explain why the grammar below that generates strings with an equal number of zeros and ones is ambiguous. S goes to 0A or 1B. A goes to 0AA or 1S or 1. B goes to 1BB or 0S or 0. To determine why this grammar is ambiguous, we need to understand what makes grammar ambiguous and analyze this specific grammar. Ambiguity in grammar, a grammar is ambiguous if exists at least one string that can have more than one leftmost drive in the derivation or more than one parse tree from the same star symbol. And what is the ambiguity in grammars? Next, let's discuss the grammar ambiguity. A grammar is ambiguous if there exists at least one string that can be derived in more than one way, leading to multiple parse trees. This is a problem in programming language design because it can cause the same code to be interpreted differently. And it's given grammar and ambiguity explanation. In this question, we have a grammar that generates a string with an equal number of zeros and ones. To show ambiguity, we will look at a specific example. Deriving the string 0101. Step-by-step derivation. Yes. Let's try 010 using 2 different paths to show how this grammar is ambiguous. Path 1. Starting from S, we go through one set of rules to derive 0101. And path 3. In second path, we use different set of rules but end up with the same string 0101. This proves that the grammar is ambiguous because there are multiple parse trees for the same string. And I think the Python code is visualization ambiguity with Python and Graphics. To make it clear, I use Python's Graphics library to derive the parse trees, each derivation. Let's walk through the code. Yes, it is code, and I'm installing the Graphics documentary and the library, but I don't use Graphics application, so I don't see the Graphics PDF, but don't worry, I'm explaining the code. Yes, this from Graphics the import diagram. Derivation tree for 0101 using two different paths. First derivation tree and explain the dot one in not h. Here's the Python code where I define each node of the parse tree and the connection between them, and display how the Graphics creates two different parse trees for 0101. Yes, the second derivation tree and one save the one dot and one derivation tree, and second derivation tree. I explained that, and this visual represent makes it easy see the ambiguity in the each grammar, as we have two distance trees for the same string. You can use the code and share the code, and the result is second derivation tree PDF, as I don't use the C. And skip to question 3. Yes. And the first derivation and second derivation. I'm so sorry. 1 minute. Because my internet is fault. I speak English or I'm singing a song, but my voice is not very good. I'm waiting. Yes. Yes. Tak. Yes. This is the code. Go to question 3. Question 3 is converting grammar to Chomsky normal form, CNF. What is the Chomsky normal form? Is the CNF? Our last question involves converting a grammar Chomsky normal form, CNF. CNF is a specific form used in the parsing algorithms, where every production rule is limited to two variables or a single terminal, and it's step for CNF conversation. Converting to CNF involves three main steps: removing absolutization production, removing unit production, and converting to binary production. I will go through each step in detail. And step 1, Step 1. What is step 1? Step 1 is removing epsilon production. An epsilon production allows a variable produce the empty string epsilon. Here we remove epsilon production by rewriting rules where this variable appears, replacing it with an alternative rule that skips the variable. An example is maybe show how S goes to AB0 change when A can be epsilon. This one, yes, and removing step 3 is removing unit production. A unit production is rule where one variable leads directly to another variable, like S goes to A. These can be simplified by replacing them with rules of the target variable. And what is the example? Example show how S goes to A is replaced with the rules for A. And step 3 is converting the binary production. It is finally, you see go. Finally, we split any production with more than 2 symbols into binary pairs by introduction new variables. Example, show how S goes to AB0 is split into S goes to AX1 and X1 goes to maybe B0 or you go to CCB. Yes, we go to Python code. Python code a bit longer, but I explain. Function 1 is define the original grammars dictionary. The grammar is I explained that. And step 1 is remove epsilon production. Function 1 is remove epsilon production. This function checks for epsilon production and removes them by adjusting rules where they appear. And remove epsilon variable says production equal epsilon and continue to add. And replace A with epsilon where applies, as you know. And the print after removing the epsilon production and grammar, And function 2 is, and step 3, remove unit production. Remove unit production. This function eliminates unit production by replacing them with the production of the target variable. And yes, it is unit production. Yes, and listed and the print after removing production, the grammar. And step 3, convert binary production. Function 3, convert to binary. This function converts the production with more than 2 symbols into binary production by introducing new variables and display each function code and explain how it contributes to CNF conversations. And I'm running this code. Yes. After remove epsilon production as B0, AB0. Yes. 0, P, A1, A1 is the checked new one. And the converting binary projection x1 epsilon and x2 x3, as you know. This is the result. Thanks for watching. Today we explored CFGS, discussed ambiguity in grammars, and convert a grammar to Chomsky normal form. I hope this video helped. I'm waiting. This printer is very uh, loudly. Yes. And again, thanks for watching. Today we explored CFGS, discussed ambiguity in grammars, and converted a grammar to Chomsky normal form. I hope this video helped clarify this complex concept. Let me know in the comments if you would like more content like this. And don't forget to like, subscribe, and share. See you in the next video.